Good afternoon, guys. My topic for this afternoon is still the importance of constant of integration. How do we compute constant of integration? Okay, before I will proceed with definite integrals, that is the integrals with the lower limit and upper limit, I will finish today the importance of the so-called constant of integration. This will be example number 2. Okay, let's proceed. The topic is still constant of integration. What's the significance of constant of integration after? In the formulation of differential equation that is needed in the software applications, because if you design software like apps, what we are using on cell phones, it's a software, okay? If you need an equation over there, okay, the equation should be with the so-called constant of integration. Okay, and how to solve that constant of integration, this will be the procedure. Constant of integration. This will be second example. I will give you a specific problem in which the constant of integration is involved. So we will know what will be the importance of the so-called constant of integration. Like in the so-called Tomahawk missiles. Tomahawk flies like that. So there should be a relation of acceleration in time, velocity in time, and in the computation of the so-called acceleration as a function of time and velocity as a function of time, we need a constant of integration for a specific design of a Tomahawk missile, something like that. Okay, I will give you an example. I will read the problem. In a certain rectilinear motion, acceleration is actually equal to 40. They give us this condition here. Acceleration is 4 times time. The initial condition is this. If s is equal to 1 and velocity is equal to 2, when time is equal to 1, find the relation between velocity and time, distance in time, and velocity in terms of distance. So actually, the problem is asking for the relation of velocity in time, distance in time, velocity and distance. In the design of the so-called projectiles, like a missile, like Tomahawk missile, these relations are actually involved. Okay, so the designer of the software for the Tomahawk missile should know the relation of velocity in time, distance in time, and velocity and distance. It's a must. So you know how it accelerates, okay, and what will be the relation of distance with respect to time at any moment. Okay, let's proceed with the solution. What is rectilinear motion? Rectilinear motion is actually motion in straight line. Motion in straight line. Like what they call this, an F-35 touching down an aircraft carrier, something like that. Okay, that's a rectilinear motion. Or an F-35 moving up an aircraft carrier, that's a rectilinear motion initially, okay? Or the movement of what they call this elevator that's going up and down. The condition should be, the motion should be in a straight line, okay? So the example on the board is actually a man, okay, walking in a straight ground, level ground, in a straight line. That's an example of a rectilinear motion. But militarily speaking, rectilinear motion is actually the motion of an F-35 touching down an aircraft carrier, something like that. Okay? The top of the aircraft carrier is actually straight line, so we could consider the motion of that F-35 moving down as a rectilinear motion. Okay, let's proceed with the solution. We are now talking like a designer, a software engineer, something like that. Okay. From the given problem, acceleration is 40. It's given. Okay. And acceleration also, by definition, is the derivative with respect to time of velocity. The differential with respect to time of velocity is also acceleration. That's differential calculus. We equate these two here, acceleration, so 40 will be equal to dv dt. Cross multiply. 40 times dt is 40 dt equal to dv. What comes out? Okay, we are now given a differential equation. What is this differential equation? This is a differential velocity as a function of differential time. Differential calculus. Okay? We just finished differential calculus. So to find the relation of velocity in terms of time, we integrate both sides. That's integral calculus. Therefore, the integral of dv equal to the integral of 40 dt. Right? We finished evaluation of the integral calculus, right? So there will be no problem. We are saturated with the evaluation of integrals. Simple. The integral of differential of b is just b. B should be equal to, we bring out this one, and the integral of t dt, it falls under the power formula. This would be t squared over 2. Power formula. Okay? We expedite a little bit. The value of u is actually t, du is equal to dt. It is exact. So the integral will be t squared over 2 plus c1. And what is c1? That is our main topic, the constant of integration. So in the formulation of the equation on design of softwares needed for rectilinear motion, an example of this is the design of a Tomahawk missile. We need the constant of integration for a specific design. For this given problem, okay, this is just an illustration, but in the actual real world in the design, okay, the procedure will be something like this, okay? So actually, the crazy person over here is actually the design engineer. Okay? Therefore, velocity now will be equal to 2t squared plus c1. Right? And what is c1? That is constant of integration, our main topic. How could we compute for the value of c1? We are given an initial condition on the problem. That when s is equal to 1, the velocity is equal to 2, when time is equal to 1. Okay? B is equal to 2 when t is equal to 1. But what will be C1? We could compute for C1 because we are given this initial condition. We put it back, we could compute for C1. Therefore, 2 equal to 2 times 1 square plus C1. C1 now will be 0. 2 times 1 square is 1. 2 times 1 is 2. We transpose that to the left, 2 minus 2 is 0, therefore C1 will be 0. Right? Therefore, the required relation of velocity in terms of time will be, we go back here. Velocity will be 2t squared plus 0, or velocity is equal to 2 times square. Okay? This is the first unknown equation in which the problem is asking for the relation of velocity in terms of time. And what's the significance of this in the design of missile? If you specify the time, at any moment, you know the speed of that Tomahawk missile. That's the significance of this. Specify 2 hours. After 2 hours, okay, you could compute for that the velocity of that Tomahawk missile. Right? That's the significance of this. That's engineering. That's the significance of mathematics. Okay. To compute for the next relation, velocity is actually the derivative with respect to time of distance. Velocity or speed is the rate of change with respect to time of distance. Velocity is ds dt. Okay? We cross multiply b dt equal to ds. Therefore, ds is equal to b dt. Right? It is b dt. But what is b in terms of time? We derive it as 2t squared. The relation here should be related to the first. Okay? So, the derived relation of b in terms of time, we could use it here. Okay? ds is equal to b dt, but from the first derived relation, b is equal to 2t squared. Okay? Therefore, ds is equal to 2t squared dt. And we are now given, or we now arrive at a certain differential equation. That differential equation is the relation of differential s with respect to differential time. Okay? To compute for the relation of s in terms of time, take the integral of both sides. The integral of ds equal to the integral of 2 squared dt. The integral of differential s is equal to s equal to 2. This is also under the power formula. We bring out this one. This will become t cubed over 3 plus c2. I put a subscript 2 over here because this constant here is not same as c1, okay? Right? So I put a subscript 2. Therefore, s now will be 2/3 t cubed plus c2. Okay? This is now the relation of s as a function of time, but there's a problem because c2 for the meantime is unknown. So for a specific design or for a specific problem, there should be value of c2. And how could we compute for the value of c2? Just bring out the initial condition. The initial condition given by the problem is the distance is equal to 1. This could be 1 mile, or this could be 1 second. Okay, or this could be, because the problem didn't specify the unit, right? But the initial condition, going back to that, s is equal to 1 when t is equal to 1. We put this value here, back here, we could compute for c2. Therefore, 1 will be 2/3 times the quantity 1 raised to the 3rd power plus c2. Okay? And c2 will be 1/3. So, for this specific problem, or maybe in the real world, specific design, the value of c2 will be 1/3. Why 1/3? 1 is 3/3, right? Right-hand side, this is 2/3. We put it on the left. This is minus 2/3. So 3/3 minus 2/3 is 1/3. So the value of C2 is 1/3. Therefore, the required relation of S now in terms of time, S will be equal to 2/3 t cubed plus 1/3. Or multiply all terms by 3, 3s will be 2/3 2t cubed plus 1. This is now the required relation of distance with respect to time. Hey guys, what's the significance of this? What's the significance of this? Supposing itong is flying straight like that. The significance of this, if you specify time over here, you could compute for the total distance traveled by that tomahawk. Right? That's the significance of this. That's engineering. Okay? This is not the relation of the total distance traveled in terms of time. Just specify the time and you can compute for the total distance traveled of that tomahawk in the real world. Okay? Let's bring out the third requirement. From the derived equation, velocity equal to 2t squared, solve for 2t squared, for t squared. T squared will be equal to b over 2. You divide both sides by 2. Okay? So 2t squared over 2 will be t squared, b over 2 will be b over 2. Then take the square root of both sides. Therefore, t now will be the square root of b over 2. Okay, from the derived relation 3s plus 2t cubed plus 1, put this value t here, back here. Okay, 3s now will be 2t cubed. Okay, sorry for this one, they should be plus 1. Okay, 3s will be equal to 2, but what is t? B over 2 raised to the 1/2. Okay, raise that again to the third power plus 1. Okay, 3s will be equal, that's just algebra. The numerator will be b raised to 1/2, raise that again to the third power, that will be b raised to the 3/2. Okay, the bottom portion will be 2 to the 1/2, raise that again to the third power, this will be 2 to the 3/2. And 2 to the 3/2 is equal to 2 raised to the 2/2 times 2 raised to the 1/2. 2/2 plus 1/2 is 3/2. So actually these two here cancel with this. So what will come out will be 3s. This will be b to the 3/2. What remains on the denominator will be 2 to the 1/2, or just simply square root of 2 plus 1. Okay, or multiply all terms by square root of 2. B to the 3/2, we rearrange, will be square root of 2. 3s, we transpose this to the left, then we rearrange, times the quantity 3s minus 1. So this is now the required relation of velocity in terms of distance. And what's the significance of this? If you specify the velocity, you could compute for s, right? That's the significance of this. We are talking motion over here. At any moment, you could compute for the value of b, okay? Or the value of s if you specify velocity at any moment, okay? For the given design. Oh, that's just an example, guys. I am just relating to the design of a tomahawk. That's a moving in a straight line. That's actually motion study. A little bit physics, but actually the foundation is mathematics, right? That's it, guys. The importance of the so-called constant of integration in the real world. It is needed in the formulation of the equation, okay, to define the motion of anything you design that's moving in a straight line. In one example is a tomahawk moving in a straight line. Okay, guys, good afternoon.